Our next type is the assignment problem. So this seems to be very similar to transportation, but still there are some difference. Let's say there is a manager. This manager is assigning n jobs to n workers, okay? So you have jobs here and you have workers here. Workers, okay? And then the assignment must be 1-to-1. So that means one job can only be assigned to one worker, and one worker can only do one job. You cannot split a job. The cost for worker J to complete job I is called Cij, okay, so it's here. And of course, we want to minimize the total cost, okay? So obviously, this is a special case for the transportation problem. Jobs are called factories in the previous problem setting, and the workers previously are called markets. Now it's just that each factory produces exactly one item, and each market demands exactly one item. So when you say there is an assignment, that's exactly equivalent to shipping one unit from here to there. All right? So this is nothing but an assignment problem, or nothing but a special type of transportation problem. Maybe you would want to ask yourself what's going to happen if the number of jobs is fewer than the number of workers. Okay, so you have several workers. You don't need to let all the workers to have jobs, but you need to complete all the jobs. Well, if that's the case, formulation-wise, it's just the same. But actually, you need to deal with this problem if you want to formulate this as a transportation problem. Okay, so if you want to formulate that as a transportation problem, well, that's not a very big problem, because all you need to do is to create a virtual supply or a virtual job or several virtual jobs, so that the delivery from virtual jobs to all your real or virtual, all your real workers has the cost of 0. Okay, so for example, suppose you have worker 0. This is a real one, and you are going to create another virtual job. And in that case, all you need to do is to say, okay, this is as a cost 0, cost 0, cost 0, and so on and so on. Pretty much, you somehow just have this virtual job to make it satisfies the requirements for transportation, for assignment, okay? The assignment problem requires you to have equal number of jobs and workers. So you create this virtual job now, so to satisfy these requirements. So let's try to take a look at the IP formulation for transportation and for assignment. We're going to say I is the set of factories or jobs, J is the set of markets or workers. So in that case, we're going to see, given our decision variables xij, in transportation problem, we may set it to be integers. Given the transportation quantities, this is our total cost. And here, for each node I, where node I means a factory, for each factory I, the total shipping quantity out from that node I should be the total supply quantity. For each market J, the total amount shipped in should be equal to the demand quantity. Okay, that's transportation. For assignment, it's simply first, your M becomes N because now you have N jobs and N workers. And the second, all your quantities are 1. Okay, because now one person works on one job. One job is assigned to one person. And finally, all your decisions will become 0, 1. So here you actually don't need to set it to 0, 1. If you set it to integers, it will still be 0, 1. There's no way for you to have 2, 3, or 5. Okay, so that's one thing. Also, please take a look at these statements. It says that if you take a look at these coefficient matrices, obviously they should also be totally unimodular. So we may put rows for I in one group and the rows in J to another group, then you will have this total unimodularity. And finally, in typical cases, we don't want those integer variables. We will use fractional variables to deal with them. But you may know that if you focus on this integer constraint for assignment problem, which is actually a binary constraint, if you relax it, then by nature, you are allowing jobs to be split. You are allowing one person to work on multiple jobs. This violates your original setting, okay? So that's why I would say relaxing the integer constraint for the assignment problem is a critical thing. If you relax that, if you want to say your xij can be 0 or 1, or any number within 0 or 1, you need to make sure that this is not going to have job split. This is not going to make a solution that really violates your constraints, okay? And luckily, we know we can do that. We can really relax that constraint because we have total unimodularity. So the last thing I want to introduce in this video is the transshipment problem. If there are transshipment nodes in a transportation problem, that is called a transshipment problem. So I'm going to skip the formulation here. I just want to show you that in general, MCNF formulation can be looked at this, right? And pretty much we have a reduction relationship here. An assignment problem is a special case of a transportation problem, in a sense that for an assignment problem, all your BI are 1 or -1. A transportation problem is a special type of transshipment problem in the case that none of your BI is 0. And finally, a transshipment problem is a special type of MCNF in the sense that there is no link capacity constraint. All right? So we can see that we have this clear reduction map or reduction relationship.